can see
Cool.
my screen.
Yeah, we can see.
Excellent. So, uh, I'll be keeping an eye on the chat, but if you do have any questions, let me know. Feel free to speak up. I know we have a Q&A at the end, but I'm also happy to take questions during if anything comes up. So, today I want to talk a little bit about some of the recent work we've been doing in my group that's been looking at how you can take processing using memory or in-memory computing and extend it across multiple application domains beyond just machine learning, and how we provide a full computing stack for that, which, in my opinion, has become essential to future progress. And the reason I bring this up is because if we look at what applications have become data-centric, there are many, many of them, from databases to graph workloads to machine learning, which are some of our sort of usual characters, to edge computing systems such as self-driving cars and drones, precision medicine, genomics, and sequencing, and even mobile device workloads. We actually did a study, it's almost been 8 years ago now, with Google that showed that even for mobile devices, things that we think are super lightweight, there's actually a huge burden of data being moved around in these devices, even for workloads as typical as browsing on your smartphone. And so what we see is there's been this shift in applications that's happened over the last, 10, 15 years. But if we look at our systems and our hardware, they unfortunately have not kept up with this. No, for decades we've been improving CPUs and now GPUs and accelerators to become what I like to call these beefy processing engines. They have a lot of cores, they're often heterogeneous, and we've optimized the heck out of them. We've made them, much more powerful and energy efficient at the same time. But the downside of this comes back to the inherent von Neumann architecture that we've been basing our architectures on for decades. And it's really designed for infrequent memory accesses. The idea, all the way back when John von Neumann was designing this, was that computation was what mattered. We did a lot of computation on a modest amount of data. And so this system is designed for infrequent memory access, where you have to retrieve this memory from an off-chip, storage device of some sort, bring it potentially through multiple levels of caches up to the processing engines before they can even start to do this computation. Now, we've recognized this for a while. We've had caches to help try to amortize the cost of bringing data back and forth between the memory and the processing engine. Unfortunately, as these data-centric applications become more complex, they're losing their notions of spatial locality and temporal locality in the ways we used to exploit them. And as a result, a lot of the inefficiencies that caches were hiding are now being exposed for these types of applications. Ultimately, what we're finding is that at its core, a modern computer architecture is still compute-centric. It's not data-centric like these new types of applications that we have. And so we're wasting a significant amount of energy and time because the inherent design forces us to move data back and forth pretty much non-stop for these types of applications. Now, it turns out that the whole reason I'm here is because the data movement is not cheap. Okay? There's this classic keynote at this point that was given by Bill Dally from Stanford and NVIDIA about 10 years ago now. And he showed that, we think of computation as expensive, but even the most expensive classical operation, a 64-bit double precision floating point operation, is relatively cheap compared to moving data around. It costs 10 to 50 times that to move data on chip, and it's almost 1,000 times that to move data from the chip over to main memory and back, vice versa. And so what we find is that this data movement is a major bottleneck in modern systems. We spend a ton of energy on off-chip communication. We have bandwidth that's limited by the small number of pins that we have on the CPU package. And we incur a high latency going between our main memory, the multiple levels of cache, and then this processing engines themselves. Now, some of you might say, hey, I've heard some solutions for that. I've seen that there are these, new products that, people have been coming up with, from UpMem to Samsung, to Hynix, where they're looking at processing your memory. And they essentially take your CPU cores or some sort of logic and move it close to the chip. It's not bad. It's a great starting point to reduce these costs. But it does not alleviate all of them. It turns out that, by and large, there's still a number of fundamental costs, such as exercising I/O inside your memories, and the constant cost of having to retrieve data from expensive, operations, such as a readout from DRAM, that are still going to be there when you move your data, processing close to the memory. And so close, unfortunately, just isn't good enough to tackle all these costs. And so this motivates us to look at what has become a more emerging approach, what we call processing using memory. Some of you might have heard the term in-memory computing, but more or less terminology problems in our community aside stands for the same thing, which is that if we look at the inherent properties of these memory devices, if you go back to sort of your essential, EE 101 class that looks at Kirchhoff's current law, Ohm's law, treats everything as sort of an RLC circuit. It turns out that the way these new memories are organized, and even ways that current memories such as DRAM and SRAM were organized, can allow you to perform operations in place. Essentially, if you turn on multiple memory cells at the same time, it won't actually short out like we might think at first. It creates chains of these RLC circuits that can actually perform useful operations. And I'll talk a little bit more about how we get it, can make that happen in a minute. And so the nice thing is, for many of the types of computation that we want to do for data-intensive applications, we no longer have to move the data to our processing engines. We can keep the data in place in the same memory cells that it's already sitting in, and we can simply do operations on them right there. One of the nice things about this is that this actually has a much greater bandwidth as well as potential, performance and energy efficiency. And that's because all of this is dictated by the structure of the memory. If I have a wide enough memory, I have that much width to do memory operations. In its extreme form, these processing using memory or PUM architectures can potentially be million to billion wide compute units themselves. And so we have scales of parallelism that not even GPUs can offer us. It's really a whole new set of opportunities that overcome a lot of the limitations of our current memory channels to off-chip compute. And I'm sure for some of you, you're saying, okay, no big deal, Saugata. I've already heard about this. You're not telling me anything new. um, because I've seen this before for machine learning. And that's true. There are a lot of uses for these types of in-memory computing, POM, that we've seen for machine learning today. I'm not going to go into too many details, but the general idea here is that in a single memory device, a memory cell, I can store multiple bits worth of information. Okay? For a machine learning operation, let's say, I'm going to store the weight inside one of these memory devices. And I'm also going to have a multi-level value that I'm going to pass in on these input voltage lines, and that's going to act as if it's the input to a matrix. And so I have my input, I multiply it by a weight, and I can get my output coming through. And it turns out that the way that the circuit is set up, we can basically take advantage of Kirchhoff's current law to perform a matrix multiply operation here. Now, this works great except for a couple of big caveats. When you do this analog operation, you're literally just doing the multiplication. In fact, you're really doing partial multiplies on this. You still have to take those partial products, you have to shift them back and forth to be able to align them to the right bit position, and then you have to add them. Those operations still need to be done outside of the memory. And so our solution for analog right now is to take these analog arrays, program the weights, and then convert the value from the current domain, which is where these multiplies are happening, into the digital CMOS compatible domain to perform the shifts in the ads. And so every operation has to deal with ADCs and DACs to be able to work efficiently. And these often end up being the bottleneck for analog. On top of that, this is great for matrix multiplication, but it's difficult to extrapolate this logic beyond that very easily. But as I sort of showed you in the beginning, there's a whole bunch of other workloads beyond just matrix operations, beyond just machine learning, that are data intensive, that suffer from the same problems. And it turns out that if we don't just do these pure analog multiplication operations, we can actually make POM work across many different application domains at once. Today, what I'm going to talk about is this different technique that we call Boolean POM. You might have sometimes heard the term digital POM. The basic premise is that I can perform bitwise logic operations using mostly ADC-free operations. And this means that I get high bandwidth, much cheaper potentially, and I can work across a large range of instructions. In theory, I can execute any program that a CPU can. One of the downsides to that is that there's a lot of potential to this, but programming is actually really difficult. And I'll talk a little bit more about what those constraints are, but our work has focused on tackling both how do we make Boolean POM practical to build, and how do we make it, easy to program, and how do we allow people to build a software stack that we can use across POM. And so toward that, I'm going to talk a bit about two works that we've done over the last few years in my research group. The first is called Racer. Racer essentially tries to abstract away the underlying device specifics to the microarchitecture. And so today, when people design their POM circuits, they often think directly about, oh, well, ReRAM has this type of property, MRAM has this type of property, DRAM has this property. I'm going to design my microarchitecture based on that so I can integrate from bottom all the way up. While that's great for maximizing the efficiency of the architecture, it turns out that then every architecture, every data path looks vastly different because it's super customized to the device. And as many of us know, it's unclear which of these existing or emerging memory devices are going to be the quote unquote winner or winners in the next few years because of production issues, because of scalability constraints, because of a number of problems that we've been seeing over the last several decades. Um, And so Racer shows that we can make a microarchitecture not care about the device. And even with that, we can use pipelining across the bits of an operand to give us high performance regardless of the constraints that each of these devices bring us. The second work I'm going to talk about is what we call the MPU, the memory processing unit. In some sense, taking inspiration from Racer, which said, hey, we can abstract away the devices, we saw another need. We need to abstract away the underlying microarchitecture itself. Think about a CPU today. Okay? You have, let's say, an x86 architecture from Intel. There are 50 years of Intel CPUs that use x86. The CPUs from, well, I guess almost 50. Um, the CPUs from, let's say, 1980 look extremely different than the CPUs that we use today. And yet, the same core interface allows you to take a program that you write in high-level language and run it in theory on both of those. That abstraction has been sorely missing for POM. Today, we sort of say, hey, if you build it, they will come. I'm going to spend decades, not decades, years building a data path. I'm going to make it the best data path with 10,000x speed up. And clearly, that's going to be enough for programmers to rewrite their entire applications for my hardware. And that is as far from reality as it can be. It does not matter how much speed up you're going to give. Programmers cannot just take their multi-million dollar software flows and rewrite them on the hope that the architecture you designed is going to be the one that wins. And so just like CPUs, all the way back from this IBM System 360 in the 1960s, figured out that, hey, we need to provide an abstraction so that I can write a program and it can work across multiple pieces of hardware. We've done what we believe is the same thing for POM, and for Boolean POM in particular, to show that regardless of the underlying data path, I can write a single program with a single abstraction that can target all these different architectures. Along the way, we've also solved some of the other, growing pains of Boolean PUM, which can allow us to handle branches, nested loops, complex control flow, and ultimately allow us to execute entire applications completely in PUM. And in doing that, that actually adds benefits over the existing architecture that we have because we've been able to add this new functionality that you could not have done without these types of abstractions. So I'm going to give a brief background here before we get into some more details here. But, as a primer, processing user memory, as I mentioned, takes advantage of these properties, really inherent electrical properties of memory arrays to be able to perform logic. On the right here, I'm showing you a little snapshot of a DRAM array. So we've got three DRAM cells here. And what happens is, instead of activating just one row like I normally would to read out a piece of data, I can activate three rows at once inside DRAM. What's going to happen is the bit line, which would normally swing up or down to adjust the voltage of one of these cells, the cell that we activated. If I activate all three cells at once, the bit line is essentially going to take a majority vote. And this majority vote will allow us to read out some function of these three cells. Now, this function, depending on if you prime one of these cells, can potentially be an AND operation or operation. And so this is just one example of how you can take memories and perform Boolean logic operations on them. Right? The nice thing here is that you can do this with little to no additional logic. And you can do this in DRAM, you can do this in SRAM, you can do it in ReRAM, MRAM, PCM. I'll show you an example of how this works in ReRAM in just a minute. This requires, like I said, little to no additional logic, but it has a number of challenges that are really dictated by the underlying structure of the memory itself, which is why often when people design microarchitectures, they do it specific to that device because they cater to those structure-defined properties. Now, as I mentioned, we've seen some of this happen before for analog multiplication. ReRAM has been sort of our canonical device that people have liked to show, for matrix multiplication acceleration. But we can use that same ReRAM to be able to perform Boolean operations. So if I take a row of cells and I float the row wire and I apply, some sort of voltage, I'm going to call it a NOR voltage. It's a logic voltage here. And I apply it to two input cells. I can then perform a two input NOR operation if I ground the column line of the third cell. And this will get overwritten with the new piece of data. And based on the logic family that I'm showing here, which is magic, those inputs will stay preserved. And so this allows us to do general purpose execution because now I have operations such as NOR that are completely Boolean, like, completely, they're Boolean complete, right? And if it's Boolean complete, I can do anything that a CPU can. The downside here is that this is doing bit serial execution. We're doing things one bit at a time. It can be extremely slow at getting these operations done. But we can make up for that by performing operations on entire columns of data at once. So we basically buy back parallelism, throughput through parallelism. Okay? In order to make this a little bit easier, the last several architectures that have come out, Racer was one of the first to do this, will often treat these as vector registers. So I can perform an entire vector's worth of operations at once across this column. And there are many logic families that can work. These logic families are specific to the underlying device and the type of functions you want to implement. Some logic families can perform NOR in ReRAM. Some of them can perform AND or NOT in DRAM. Some of them can perform imply NOT, NOR NAND, NOR NAND XOR. There's a whole bunch of these families that exist. And for each of them, they have their own voltage and current settings, and they depend on certain device characteristics to make them happen. And the reason this works in something like ReRAM, for example, is because ReRAM stores its data as a resistance and organizes these cells as a cross-point or a cross-bar array. And so each junction between a column line and a row line contains a selector device and a resistive memory switch. Now, if I gang operations together, for example, if I perform, the that logic operation across multiple columns, I can essentially do parallel NOR operations here. So, if this sounds great, you must be saying, well, Sagata, this is too good to be true. Why don't we do this, right? Why are we not seeing prototypes of this? Well, there's three key reasons for this. The first is that programmers are stuck with only these fixed width vectors. Okay? However long my column is, that's going to be the size of my vector register, and that creates a couple of problems. Excuse me. Real applications have varying degrees of parallelism. It's not just one fixed parallel set of operations all the time. Vectors are also notoriously difficult for control flow. We already see some of these problems in GPUs, which aren't true vector machines, but they use some properties that have inherited from themselves from vector operations from decades ago. And the more wide a vector is, the more likely one column of vector data is supposed to diverge in terms of operations, if-else statements, for loops, things like that, from other columns. And so this creates a lot of difficulty as we're dealing with these fixed width vectors because they were never designed to give us the flexibility to account for that. The second thing is that programmers have to account for what are often device-specific and architecture-specific resource constraints. For example, several architectures, and I'll show you how this is true in Racer as one example of this, need to time multiplex different resources. We see this in memories all the time, right? Our DRAM, for example, shares a single memory channel, a bus, across all of its different banks. One of the things we see that's a little more problematic in Boolean PUM is thermal throttling. These Boolean operations, while they're very powerful, can consume more current than other types of operations we see in memory. And so, in order to avoid hotspots within the chip, we find ourselves practically having to do some thermal throttling to ensure that we're staying within reasonable thermal dissipation capabilities of chips. Okay? Again, today, what do? We say the programmer can worry about that. Not exactly a great thing for someone who's used to being a software engineer to have to worry about, to think about, well, where is my chip going to get hot and cold? The third thing is that programmers just don't have a software stack that they can use. Every data path requires its own custom bespoke software. And that's because each data path looks different. It uses different devices, it exposes different operations. It doesn't really think about reusability, right? Everybody writes a paper and designs a data path, assuming that, well, of course I wrote the best one, that's why I wrote the paper. The reality is that as much as I'd like to think I have the winning architecture, like maybe you would, we don't know which is going to be the winner. And unfortunately, until that winner gets decided, no software developer, nobody who's writing an operating system, a programming language, a compiler, is going to take a bet that architecture X is the winner and that I'm going to write all of my software to cater to architecture X. So, this lack of compatibility creates a problem, but it also means that because we don't have software today, we can't even write large applications that can take advantage of this parallelism without painstaking effort. Because we're often thinking in, you know, the equivalent of assembly instructions and writing everything by hand and sequencing and coordinating all this manually as programmers. These are big, big barriers to somebody using any piece of hardware. And to me, this is why Boolean PUM has been really difficult to, to take advantage of today. And so the question that I want to ask for the rest of this talk is, can we use abstractions to hide these barriers? Can we hide enough of these specifics without losing the performance benefits that we have so that we can still get meaningful benefits that we can expose? And so I'll start by talking a little bit about Racer. In Racer, we set out to solve some of the problems that come with this bit serial operation that we have, right? And so, just as a quick refresher, a bit serial operation performs one bit at a time. The canonical example of this is a full adder, where we calculate bit zero, we calculate the sum for that bit as well as a carryout. We pass it to the next adder, bit one, and we calculate the bit one sum and carryout, and we do this for every bit in the operation. A ripple carryout is slow, and just like it's the exemplar, bit serial operations can be painfully slow. Right? We can implement a lot of different operations with them, but these long latencies create problems. And so these Boolean PUM architectures, sometimes with the term digital PUM, work on entire columns of data, as I just showed you, to exploit data level parallelism. So if the bit serial operation is slow, let's just do many bit serial operations at once. And so in the past, architects said, great, I can make large arrays. I'll make really large columns and I'll do all sorts of operations. Right? And for a few years, there were a lot of research works that were advocating for exactly this. But when we took a look to try to understand, okay, that seems like it doesn't really um, gel with what device folks have told us. What we realized was that there was an actual problem that was happening. For these whole column operations and something like in most of these architectures, the more columns you the that you sorry, the more rows in the column that you have to do your operation, basically the more parallel operations you're doing, your current is growing proportionally. So if I make my tile much larger, the current becomes much larger. Unfortunately, what happens is if you make the columns large enough, that current is going to be so high that it's actually going to create electromigration problems and damage the metal wires that are in your memory arrays. Perhaps the most extreme example of this is ReRAM. In ReRAM, we did some, analytical modeling, and we found that to avoid electromigration, you couldn't use more than 200 by 200 arrays. Okay? People were proposing thousands upon thousands of rows, thousands upon thousands of columns when we were looking at these past architectures. They're just not possible. And so one of the problems is that when we look at these small tiles, we don't really use them in memories. And that's because, well, for Boolean PUM operations, we don't get enough amortization. There's not enough parallelism to buy back that extreme latency of bit serial operations. Even in conventional memories, we've not used small arrays because we get really low densities. For each array, we have to have peripheral circuitry, control circuitry that has to come along with it. That takes additional area. In fact, today, if you look at DRAM, the limiting factor of how you scale up area-wise isn't the array itself. It's the sense amplifier that's reading out data. I can't afford more of those, but yet the smaller arrays I have, the more sense amplifiers I need. The smaller my arrays are, else I need to communicate across them. I need to coordinate, and tie them together. That creates these difficult to scale networks as well. So small arrays have conventionally just been a big, big problem. And yet, as we saw, that's the only thing we can do to build a cell safely. So with Racer, what we set out to do was to ask the question, is small tile PUM even feasible? Or is this really just the end of the road? And what we figured out were a number of tricks that could actually allow us to overcome these barriers. Where at the time, state-of-the-art architectures would keep, whole chunks of a word, if not the entire word, in a single array. That was sort of the way we've done this for a long time. In Racer, what we instead said was, what if we just distribute each bit of a word to a different tile, a different memory array? And what we realized was this could enable a whole new type of execution model across these small tiles. The next missing piece to this was, okay, well, if we keep the bits in different tiles, I will do my bit serial operations one tile at a time, and then I need to pass the carryout to the next tile. So we created these VRAM-based column buffers that could allow us to take one column of data from a small array, move it through a buffer into the next array, using pass transistors on either side to make sure that when we connect them together, we can still use ReRAM in the center column so that we're not having to do an ADC to DAC operation. But with more ADC and more ReRAM cells, I can potentially have electromigration. So instead of tying two arrays together and introducing electromigration opportunities, we isolate this buffer so that it only works on one side. So in this first operation, the buffer is electrically tied using fast transistors to the tile on the right. And then when we're reading out of the buffer, it's only electrically tied using those pass transistors to the array to the left. This allows me to basically have an n plus one array operation, keeping electromigration manageable. One of the other nice things about this is that if you're familiar with CPU architectures, that buffer kind of looks like a pipeline register. It can store intermediate data before we move on. And so we take advantage of that and borrow this concept from CPU pipelining across instructions to instead do pipelining across bits. And so on this diagram over here, as we go down, we're going further in time. You can imagine it's cycle by cycle. Let's say I start for an addition for group of additions A, and I'm going to start on bit 0. I'm going to generate a carryout. I'm going to perform the next no addition. I'm going to generate a carryout for bit 1, pass that over to the next tile. Then I'm going to generate a carryout for 2 and so the summon carryout for 2 and so on. What you'll notice here is that while um, once I finish the operation for bit 0, that tile is now sitting idle. It's not doing anything while bit 1's operation is going on. So what I can do is instead perform a second addition behind it. And it doesn't have to be an addition, it can be any operation. And so I can perform that operation's bit 0 in parallel with the earlier operation's bit 1. And then I can keep cascading this bit by bit where I can perform the next operation's bit 0 while other arrays in the pipeline are doing bit 1, bit 2, and bit 3. And so this allows me to execute a high throughput of operations back to back without having to wait on just the latency of bit serial operations. And so with T tiles organized together, I can operate on T columns of words in parallel instead of just a single column like we used to. Now, what we see is that based on this, we have this architecture that allows us to do bit by bit operations, but pipelined in parallel. We can go one step further because, as you saw in our ripple carry example, it's the same operation that we're doing again and again. It's essentially a bit serial addition. So why do I need to generate a new command for every operation I do? If you notice back here, one of the things that we did was when I positioned the words of a data in Racer, I made sure that the bits were always in the same row and column of each of the arrays. What that means is if I generate a set of commands to do the single 1 bit's worth of sum and carry out calculations, I can reuse that same exact command on the next tile. So as we pipeline our data, we can also pass along our instructions in the pipeline manner. So I only have to generate an operation once, and then it gets passed from tile to tile to work on each new bit of the operation. This significantly reduces the complexity of control path that I need to get this architecture to work. I have to generate only a single instruction for an entire or no pipeline of these arrays. One other nice thing about this architecture is that I can group this into what we call a byte group, and I can support operands of different widths. I can support 8-bit operations, 16-bit operations, 32-bit, 64-bit operations, which maps with the different types of data types that we see in high-level programming languages, because not every operation is going to be a 64-bit addition or a 64-bit comparison. Now, one of the other advantages that we see with Racer is that we can actually scale things up very, very cleanly. Okay? So we take the cell, and we already showed you we take, no, we can organize a cell into tiles. And then I can take this tile and organize it into a pipeline, okay, as we saw. And I'm going to have some control circuitry for the pipeline that allow me to have queues of instructions that get passed from tile to tile to move along with the bit serial operations. Now, what we do is we amortize this control circuitry across a number of pipelines at once, both to save, to reduce the control path overhead, and to allow us to implicitly manage thermals here. And we form what we call a cluster, essentially 2 MB of ReRAM that can execute one pipeline's worth of instructions at a time. Now, this cluster is actually reasonably small to the point where, depending on the needs of your end platform, if I want to build a large, ReRAM chip for a data center or a small one for, let's say an embedded device, I can scale my chip up or down based on however many clusters you want because each cluster operates independent of one another. In order to make communications happen efficiently, we implement a two-level network that I'm not going to get into too many details of in this talk, but allows us to efficiently communicate across these different clusters. Now, I'm not going to focus too much on this as well because we've since replaced these abstractions with what we have in the NPU. But the basic idea is that we can expose each pipeline as its own racer core. We provided a vectorized ISA, and it could allow us to perform a number of different operations to execute, reasonably healthy kernels. But that initial work, the work that we did for Micro, had one, what I argue is flaw, the same flaw that these other works have. It's specific to a device. In fact, the R in Racer originally stood for resistive, and so we focused on ReRAM. But as I mentioned, that has its drawback, which is, well, if I want to build this device out of anything, or if ReRAM doesn't succeed, I'm out of luck. And so in our follow-up work in JetCast, what we realized was that we don't have to be reliant on a specific device technology. Here, for example, I have ReRAM cells with using the Magic Logic family, which was developed by folks at Technion about a decade ago, that allows you to do NOR inside ReRAM. Right now, I have to have all of my controls in my pipeline control circuitry specific to ReRAM to make this work. But instead, what I can do is introduce a thin layer, what we call a technology interface circuit, that contains essentially just the specific voltage and or current drivers to take a generic instruction that's coming out of the racer microarchitecture and translate what that NOR should be into specific voltages and currents that operate on the array itself. What this means is that, except for this thin layer, this technology interface circuit, everything else in Racer can be the same across all the different types of architectures you use. You no longer need a ReRAM specific racer or a DRAM or an SRAM specific racer. Everything is the same. You just swap out your different technology circuit for the different type of device and logic family you want to use. You can even make it programmable if you wanted to, if you want to swap in and out different devices and make chiplet style architectures. So this simple concept allowed us to decouple the hardware of the device from the hardware of the data path. One of the other things we found was that Magic, while it has been really useful to ignite a lot of research, was unfortunately incompatible with the direction that ReRAM had gone in commercial processes in the last few years. So in this graph, I'm showing you the ratios between the logic operation, like our NOR voltage, and the set voltage for a resistive device. On the y-axis, I'm showing you that same ratio to the reset voltage. If you read the Magic paper, and Felix builds upon this, so it also follows this, those logic families require a certain setup of reset and set ratios that puts Magic and Felix in this top left corner of this graph. Unfortunately, if you look at what commercial ReRAM processes are going towards, your typical device is in the complete opposite quadrant of this. This motivates us to think about, well, how can we use there's commercial devices to be able to do magic-like operations. We actually developed a new logic family called Oscar that's compatible with the bulk of these devices that are being made today and is easy to shoehorn into existing commercial processes. I'm not going to go into too much detail of it in terms of time, but direct you to our JetCast paper where you can see the way we set up our cells and what voltages we use to make NORs, non-destructive NORs, and destructive OR operations possible. Now, with Racer, what we see is that we actually get significant improvements over both the multi-core CPU and what at the time was a state-of-the-art GPU. Um, no, we got large energy savings as well as performance improvements. Um, that inspired us to take Racer and see if we could actually design an SRAM version of it. So we were intended to take this out. Unfortunately, due to some stage hiccups with the memory compiler of the tool flow that we had to use, we could not take this out, and so we're hoping to do that soon. But we actually used the state-of-the-art 60 nanometer process to lay out a an SRAM based racer. For the sake of simplicity, we implemented a subset of our instruction set architecture, but it used Oscar-like properties inside SRAM to be able to perform the logic. What we found was that even for SRAM, which has much poorer density than most any other memory that we're going to look at for PUM, we can still get 60% of the performance of, again, at the time, state of the art is an RTX 4090 GPU, but we can do those same operations with only 7% of the energy that the GPU was using. And that's with SRAM. Again, other technologies will give us much better energy than that. And so Racer gave us a chance to be able to make this device compatibility work very cleanly. But that was all on the device side, right? We made the device agnostic, but then you still have to use the Racer microarchitecture and the instructions and everything that comes with it. We wanted to go one step further to solve the programmability issues and give people a chance to say, okay, well, Racer is cool, but what if I want to do MIM DRAM or simple MPU or something of that, simpler PIM or some other architecture? We wanted to provide a way for programmers and software developers to not have to worry about which architecture, which microarchitecture data path they're using. And again, part of the problem is there's just been a lack of effort. People have been so focused on designing the data path, right? Or no, the microarchitecture of how I perform the operations, that very few works even talk about how to control that data path. And yet even fewer works talk about the software to run programs on that data path. Whatever software that does exist is completely bespoke to a specific microarchitecture at the moment, or requires significant customization of middle-end software tools to cater to a specific architecture. And they're often specific to a single application domain. And so one would say, okay, well, we have a host CPU. Can we use it to maybe help us take away some of the more complex operations, run our software stack, maybe handle control flow that a control path would have to do? But we did a quick study, and it turns out that um, even for loops that have a lot of computational operations in them that don't require control flow, um, so let's say we have a for loop that has 80 instructions inside the loop. Control flow should be a small blip, right? Turns out even in that case, for this 80 instruction loop, you can spend tens of thousands of cycles performing just the loop condition on the CPU, simply because of the overhead of sending things back to the CPU to evaluate the for loop, to do the control flow, and to communicate back and forth for each of the PUM lanes that you have to perform in parallel. And so by doing this, we're actually wiping out our PUM's benefits versus a GPU. And so this is one of the things that I think we've lost some vision of, that offloading can undermine most of the benefits of PUM. And we see this time again, we've seen this in some other works that we've done in the past, that we can't keep relying on the CPU to fill in the gap anymore. And so that's what inspired us to create the MPU, the memory processing unit. Just like the CPU has its own abstraction and some expectations, the GPU model has its own abstractions and set of expectations. We wanted to create the same thing for POM. And so the MPU essentially gives a reasonable, substrate that can allow for end-to-end application execution and an interface that we can build a software stack on top of that can allow it to work across most Boolean POM data paths. And so we built this on top of the vector register file interface that most of these architectures either do use or can be uh, easily organized to make use of. The MPU introduces this new concept called ensembles that lets programmers choose which data in a microkernel should be executed at any given loop. And the choice of data is not tied to any specific memory array or any specific physical entity. We essentially allow programmers to tell us which data should be used across the entire program. A runtime and our control path hardware will actually take that ensemble, just like a GPU runtime does today. Only here we'll figure out across all of our different hardware constructs which vector register files, which pipelines should be activated at once, and which ones should be serialized to make sure we have correct execution. To make all this work, we had to design a control path. And so we went ahead and designed the circuitry for control path that not only interfaces between this abstraction that the programmer sees and the underlying data path, but it actually allows us to add more functionality such as the end-to-end execution than we've ever had before inside a POM chip. In order to make this work, we actually built, and it's not quite a compiler, it's really an advanced assembler that can allow us to make it really easy to program large applications on the MPU. We call it EasyPin. When we put all this together, we showed benefits across three different POM data paths with three different device technologies underneath them. For Racer, we were able to provide about an 80% improvement in performance and a 3x benefit in energy over the original Racer work. So on top of the benefits you saw before, we've got even more benefits because we got rid of the offloading bottleneck that POM has relied on for since its beginning, more or less. And so, just to give you a little bit of a flavor of what the MPU does, the first question we have to ask is what does an abstraction need, right? If we're going to expose something to the software programmer, what should they be able to see? Well, as I mentioned before, programmers expect flexible degrees of parallelism. They want to write the type of parallelism that exists in the program. They don't want to be forced to contort to the only type of parallelism that a piece of hardware offers. Right? That's where our ensemble model comes in. A programmer can just say, this ensemble maps to these pieces of data, these registers, and then we'll handle how those pieces of data are mapped across the architectures and how we group them together to do parallel execution. A programmer should also never have to think about hardware constraints, right? As I mentioned before, we have all sorts of things like thermal constraints that exist in POM today. For example, in Racer, when I look at my cluster, I can only have one pipeline active in the cluster at a time. With some slight tweaks, turns out we can have two active at a time out of 64 different pipelines that we have in the cluster. I don't want a programmer to have to think, okay, well, I have my data here and I can only turn on two pipelines at a time. So I have to write this and sequence it with some sort of synchronization primitive before I move on to the next two pieces of data in my pipeline. And so we defined another concept called a register file holder that groups vector register files that share resource constraints, be it physical constraints such as wires, thermal constraints such as I can only activate X of these at a time, communication constraints. All of those are embodied in these register file holders. And so the runtime can know that within a register file holder, it has to obey certain constraints, but ensembles can stitch however many register file holders as they want together, and however many vector register files inside those register file holders together, and the runtime will manage which ones execute while obeying intra-RFH constraints. We also want to maximize our binary portability. Um, we already talked about EasyPIM. Behind EasyPIM is an ISA of, I believe it's 46 or 47 instructions. I'm not going to bore you with it here, but you can look at our HPCA 2026 paper to see what those instructions are. We picked those instructions as a combination of operations that would enable this ensemble execution, instructions that would encompass a wide degree of operations that we want to perform, and instructions that could be implemented across all of our different data paths based on their underlying logic families and device technologies. And finally, as I mentioned before, we want to avoid those frequent off-chip CPU requests. And so that's where we designed this control path that can handle a lot of the operations that the CPU had to get involved with in the past. And all of this gets managed by a runtime that's coordinating the execution across an entire chip of MPUs. And so, as I mentioned, we've mapped this across multiple data paths. We showed three different ones in our paper. Um, with Racer, we call a cluster, we assign each cluster to its own register file holder. A vector register file is one pipeline. And within that pipeline, one column of data is a register. With that, we can naturally execute bit pipelining. But the MPU doesn't care if you're doing bit pipelining or not. For example, the MIMDRAM architecture, I can take the parallel mats and say that each mat is its own vector register file. Each microprogram processing engine, which can run on multiple mats within a chip, is its own register file holder, because that's where the only constraint is for execution. And that the registers are rows of DRAM cells. And in duality cache, I can have a similar mapping where the register file holder corresponds to one window and its corresponding SRAM arrays. And within each SRAM array, I assign it its own vector register file. This whole register file holder mapping, we chose it intentionally because it maps across the vast majority of Boolean pump data paths that we've seen to date. And we expect to be very flexible for future mappings as well. The nice thing about this is that these mappings are all decided at design time. The programmer doesn't have to think about this. When I design a microarchitecture data path, I can figure this mapping out, and that can just become the universal thing that gets used for this chip. Now, when we're writing a program, we use EasyPIM, which is a Python-based assembler. You can extend this to have a full compiler. In fact, that's one of the things we're hoping to do in the future. Um, but what this does is this generates, uh, you know, a file of MPU ISA instructions. The EasyPIM allows us to express for loops, if conditions, all sorts of things directly in line with assembly instructions. Okay? We can support macro function expansion. We can support functions. We're doing a lot of lifting that we would like to see in future versions of compilers already in an EasyPIM. And then EasyPIM takes that and maps it across multiple MPUs and figures out how each register file holder is assigned a piece of data within that. Um, as I mentioned, it supports all 46 MPU instructions. EasyPIM can actually work for non-MPU data paths as well, but we stick to these MPU instructions for now, for the sake of this talk. Next thing is, well, a programmer does need to define an ensemble and say which pieces of data are going to have the same operation performed on them, and they need to know how to parallelize them. So we fully define this in the code that gets passed into EasyPIM. Okay? EasyPIM can declare ensembles, and it kind of looks like a lightweight thread without actual hardware support for threads. Okay? So we have these compute ensembles where we can say we're going to turn on certain register file holders and vector register files. Okay? And all of the vector register files that are activated are going to run the same code, the same body. Now, because of constraints, they may not be able to execute at the same time. The runtime will figure out the actual execution of them. But the programmer says, I've got this loop body. It should apply across these three vector register files. And if you want, you can execute them all in parallel. The nice thing here is that this uses shared memory semantics, so we don't have to worry about this explicit dependency management. Because we assume once a compute ensemble is done, its operations will be visible to all memory in the chip for the next and subsequent ensembles. If we need to force a synchronization operation, we do have explicit sync operations to add a memory fence. And we also add transfer ensembles that can allow us to take data out of any one vector register file in the chip and move it to any other vector register file in the chip. And we can do this, either on vector registers or even on potentially single pieces of data if we want to. Hmm? And then we also include operations that move within an MPU and operations that move data across multiple MPUs. And so again, how you structure the MPU, like how many of these register file holders are assigned to an MPU, that is a design time decision. For example, with Racer, we chose to have 8 Racer clusters map to one MPU. And so that 4096 cluster chip, we also use a ninth cluster to hold the data. That could map to roughly 450 MPUs on a single chip here. All of those being coordinated by a single binary that we write. We also provide support for in pump control flow. We take advantage of conditional registers that store the output of a mask operation, and we can copy the conditional data into a mask register that directly controls the voltage lines for each row. And so I can essentially do the equivalent of power gating on rows of the memory at a time. And so when a loop ends for one particular row, I'm going to disable its mask bit and keep the other rows running until they terminate their loops as well. And so one of the classical problems, branch divergence, that we see in GPUs, we can actually solve efficiently here by using these masks to directly control the voltage lines going to the arrays. And our control path, which I'll show you in a minute, has some evaluation infrastructure to calculate loops, if else statements to do them with nesting. With the nice thing about this is it directly reads data generated in the vector registers themselves. So if I want a nested loop, I can just calculate it inside the array and pass it to the mask register. And so you can see a few examples of some code that we do here. I'm not going to get into these in the interest of time, but I can retrieve masks, I can modify masks, I can set them, I can compute on them however I want to, just like I can any regular operation, which gives me a significant amount of flexibility with how to control operations. In fact, with these masks, I can even do scalar operations inside the array because I can turn off all but one row when I do an operation. Now, to make all this work, we have what we call a universal. I'm putting it in quotes because, somebody could come along and build something that looks so different that it doesn't work here. But we believe it's compatible with almost every Boolean PUM architecture we've seen so far. And this control path includes a precoder that actually fetches, instructions from instruction storage, which is one of the big things that most PUM architectures forget about. It takes energy and time to retrieve an instruction. It has to be stored somewhere in the chip. Okay? We have compute controllers. We have multiple controllers in an MPU that can each control its own programs. This gives us the equivalent of multi-program execution. Okay? Here, the runtime interacts with the compute controller to perform the thermal-aware scheduling of instructions. It can buffer instructions. We can perform the instruction decoding into the micro-ops that are specific to a particular device. And we have an activation board that can figure out how we can parallelize operations across, within a compute ensemble. We also have a data transfer controller, which manages the movement of data within and across MPUs. But I want to focus on a couple of optimizations here. One is what we call our recipe table. One of the things that we see is that I have an add instruction, and that's going to generate a bunch of no ops. Sorry, a bunch of micro ops. Those micro ops are dependent on a specific microarchitecture, right? In Racer, that happens to be an OR. In MIM DRAM, that can be and or not. What we do to enable flexibility in the data path is that we have the ability to read templates for these instruction to micro translations from memory and do operand substitutions so that we can make this very efficient. We also see that several instructions reuse the same micro-op sequences. For example, an addition versus a multiply accumulate. The accumulate part is just going to be an addition. So to reduce the amount of space that we need for this and to be able to decrease the circuitry, the complexity of the circuitry needed to do the decoding, we overlap these operations. So a Mac, you'll see here, uses 60 micro-ops. The add uses the last four micro-ops of the Mac to implement just the addition part. And so this allows us to compactly make the most efficient use of our storage area for our operations. And so our instruction goes through, we look up a pointer table that tells us where the template is to decode that instruction into micro-ops. And then we pass in our operands into a template filler to be able to substitute for each source and destination in the uh, micro-op sequence. Now, to close up, we do these evaluations. We again compare it to an RTX 4090 GPU, was the state-of-the-art GPU we had at the time. We show our changes across three data paths, and we do this using Mastodon, our group's cross-stack simulator. I'll talk more about Mastodon real quick at the end of this talk, but it's this, you know, simulator that's allowed us to do modeling from architecture level decisions all the way down to low-level transient accurate device modeling. And what this has done is given us a platform to be able to do cross-stack research very easily to enable these types of projects. Um, this has almost become a meme in my group because we are behind with it a little bit, but we are finally on track to release a new version of it at the end of this month. So that should significantly clean up the code and add a bunch of functionality here, which we're hoping to keep growing in the coming months. What you can see is the NPU, even with its complex front end and handling of control flow, has pretty reasonable area and power footprints. And we see that it speeds up existing architectures. So here, the speedups are relative to their starting architectures. So, the y-axis for each bar is normalized to what the speed up on, let's say, Racer or MIM DRAM would have been, the performance before the NPU was added in. And so what we see is that all three of these designs see benefits of performance improvements across their original non-NPU designs when coupled with the CPU. And that across the board, we can provide significant speedups over that RTX 4090 in combination of these data paths along with our NPU's control path operations. When we compare to the energy as well, we see significant savings. In large part because we're saving the offloading going off to the CPU. We're buying back that energy that was being wasted on that CPU and PUM communication. And so we can get anywhere from 2 to 4x of an improvement in energy savings over the old architectures that we had before. And again, this corresponds to notable savings over the GPU itself. Finally, I would no. You can see here that we can actually execute real-world end-to-end applications. We implemented the encoding stage of an LLM. We looked at Black-Scholes, which is a financial program, and we looked at an edit distance calculator for genome sequencing. And we can see that, it doesn't always beat the GPU, but in every case, compared to the non-NPU version, the NPU provided a significant improvements over the original data path by buying back that communication. And again, we couldn't even execute these without doing things in no, without the NPU. Now, the solid bars, they don't rely on the CPU at all. They're doing all these operations strictly in the PUM chip. So, some quick closing thoughts. I know I'm a couple minutes behind, so I will try to wrap a little more quickly. Um, no, in this talk, I hope we showed you that there's a need for these abstractions, that racers, device level abstractions, and the NPU's sort of architectural interface abstractions can provide us not only with significant new functionality with large performance and energy gains, but also ways to take away the specifics that we've been designing PUM architectures with for much of the last decade and a half, so that we can finally be able to build reusable flows, reusable data paths, reusable compilers and operating systems and programming frameworks that we desperately need if we want the rest of the computing community to come along with us for the ride of Boolean PUM. Now, if you've seen a talk of mine before, you've probably seen this slide in the past. These are what I'd argue are big pump playgrounds. We've done a lot of work with these things that have enabled a whole slew of new research directions within our group, and we hope also for others to be able to take advantage of. So to me, they're really pump playgrounds. There's starting points of lots of work, lots of future research that can happen. But it required extensive collaboration up and down the stack. And I think three things that we should focus on to keep that type of collaboration going is that aim for broad solutions. It's very easy to take the application specific way out, right? I'm going to build a PUM architecture for this specific LLM. I'm going to build a PUM architecture for this specific genome sequencing pipeline. There are innovations that come from that. But the stuff that's more likely to be built, the stuff that will break more ground, in my opinion, are solutions that aim across multiple applications and ideally across multiple domains. Because these are reusable ideas, they can make, you know, a chip whose engineering costs are finally justifiable to industry, right? It's one of the downsides of ASICs. ASICs are really hard for commercialization because there's only so much of a market you can tap into. If you broaden your chip architecture to many, many different domains, you're taking all those different markets and putting it together. And as much as researchers, we want to think about our ideal world where these financial constraints don't matter, if you want these types of chips to see the light of day, you have to start thinking in terms of what can I make it, what can I make so that industry finds this palatable? And this is one of the big things. But don't ignore programs, don't ignore the programmer, right? We need to get beyond, well, I gave you 15,000x speed up, you should care now. And we need to try to make ways for programmers to make, easily approach this hardware. Several people propose domain-specific languages as one solution to this. I think that's a step too far. And that's because just like having to rewrite your program for the assembly instructions for a specific microarchitecture, I shouldn't have to rewrite my program with a specific DSL to get my benefits. Because, again, unless you can promise me that I'm going to get a gain, I'm not going to spend millions of dollars rewriting my code base for you, right? I think DSLs will be the way of the future after PUM becomes commercialized. But for us to get commercialized first, we should really think about using as familiar an approach as we already can. We already embodied some of that in the MPU, not using new abstractions, not using new programming uh, models. We tried very much to stick to things like threads and loops that are familiar to existing programmers, because the more easy it is for people to take their existing code and come on board, the more likely it is for this to see the light of day and to not die a premature death. And finally, the last takeaway I want here is abstractions are important. They enable cross-stack research, they enable compatibility. We've been ignoring this for a long time as a community, right? My hope is that in showing you the things that we've done with Racer and the NPU, you can see that there are benefits, that abstractions aren't just a waste of time, that they can actually give you improvements as well as flexibility for the future. Okay? CPUs, computers went through this decades ago, right? Like I said, the System 360 was the first to do this. Up until then, every computer you built, you needed a new program that had to be written and you had to redo everything from scratch. We learned that lesson decades ago for CPUs. I think we need to learn this as the pump community as well today, because otherwise the same problem is going to happen where that rewriting is going to be so inefficient that people won't care to come. The nice thing is, as architects, as hardware designers, we can use these abstractions as our way to drive collaboration up to the software stack and all the way down to folks working on materials, devices, and physics. We've seen successful examples of that in my group in the past. I mentioned Mastodon. You can see briefly here the stack that we have. It allows us to model many different types of underlying memory devices with Verilog A encoded device physics, and we can simply take those and pop them in directly and actually model how end-to-end applications work with those different devices. This allows us to work hand in hand with device designers building early stage devices to figure out how to build memories and PUM architectures out of them. Another work that came out of this that we just published a few months ago at ASPLUS is Darth PUM. It enables what we call hybrid PUM. Now, I talked about Boolean PUM being great, but admittedly, analog PUM is still better for those matrix operations than Boolean PUM. Boolean PUM is just more flexible. And so, what if we had a best of both worlds solution that tied these things together? That's what Darth PUM does. It has analog PUM arrays, digital PUM pipelines, and it shows how you can integrate them together in an efficient way to be able to enable all these operations plus more in an MPU compatible way. And we get large benefits in terms of throughput and energy for a number of matrix-based operations. And that's just a sample of some of the things that are going on in Arcana, my research group. If you're interested, you can go to the website. You can learn more about this. You can reach out to me. We're happy to talk about things. But you can see that we're really doing things across the entire stack in ways that I think would be really impossible to do had we not had this framework and this mentality to be able to let us collaborate widely from top to bottom. Because at the end of the day, our goal is to build the entire computer stack because somebody has to do it. So, with that, I want to thank my two PhD students who drove the bulk of the work they talked about here today, Min and Yicho. If anyone has full-time positions, Yicho is going to be on the market, likely at the end of this coming academic year. So, reach out to me. I'd also like to thank our sponsors who, without whom this work would not have been possible. And so, with that, finally, I'll stop here and take any questions. So, thank you for your time, everybody.
Thank you very much, Saugata, for this very nice talk. Indeed, let's take the questions. Any?
Subscribe the channel to get the instant updates on our webinars.